I'm Rhys Davis. I'm a second-year master's student in the Energy Systems program, the Energy Graduate Group here at UC Davis. I'm also a graduate student researcher for the UC Davis Energy and Engineering Office, and a graduate intern at SMUD, the Sacramento Municipal Utility District. And I'm going to be talking about the opportunities and barriers to SMUD multifamily electrification / decarbonization. So, why multifamily electrification? So as many of you may know, electrification is a key aspect of SMUD's decarbonization strategy. We're looking to electrify all residential buildings by 2045 or so. And about a quarter of these meters are multifamily. And there's some specific issues there. You know, there's more likely to be renters in multifamily buildings, which creates some split incentives. Because the building owners must kind of bear the upfront costs, but don't pay the utility bills for the most part. There's more affordable, or most affordable housing is multifamily. And so there are kind of specific opportunities there to target electrification of affordable housing, like government subsidized housing. And there's also some challenges around central water heating. So there haven't been many examples of central heat pump water heaters installed in existing buildings. Just like a few in SMUD territory and really not that many statewide. So it's kind of a new challenge that we're looking at. So it's worth focusing on. So here's kind of a current look at what SMUD multifamily building stock looks like. Most of the multifamily meters are kind of populated downtown, Arden Arcade area, kind of on the northeast side, and Rancho Cordova there on the east of downtown. But the kind of multifamily meters per capita, so like kind of the highest density of multifamily housing is that downtown, just northeast of downtown area. And it may be interesting and specific to Sacramento compared to other California cities, most of the units, the multifamily units are in buildings that are less than, 35, 36 units. So it's not, you don't have most of your multifamily units in these high rise, like 100-unit buildings. It's mostly in your, low rise kind of garden style apartments, which I think is worth noting, and then a few fourplexes as well. So also worth noting that about a quarter of multifamily meters are on SMUD's low income rate. About 17% are in communities kind of considered disadvantaged communities based on the Cal and Biro screen, top 25 percentile. And around 12% are in low income housing, government subsidized housing complexes. So the objective for my research is to first identify or predict kind of the fuel and system type for domestic water heating. So that's either going to be gas or electric resistance for the most part. And it's either going to be central, multi-central, or individual. Multi-central is a water heater that serves multiple units, but is not recirculating. So it's just kind of a standard, but perhaps a little bit larger storage water heater. Also doing this for space heating. So whether it's gas or electric resistance, it might be a wall furnace, or it might be a central hydronic system, so central or individual. And then cooking fuel. Do you have a gas range, or is it like an electric stove? And so based on those results, I'm going to add the projected electrification loads, like as we begin to electrify more, kind of what is it going to look like to add on these loads from electrification, and determine what that's going to do to the electrical infrastructure. Is it going to overload the transformer, the distribution transformer, the main service panel in the building, the unit level panel, and kind of what are the costs associated with that compared to the costs of the full project. And then from there, we can begin to kind of target neighborhoods to prune the tree, as they call it. So like targeting neighborhoods that have a high density of gas infrastructure, low costs of projects, and you can kind of begin to trim away at the gas distribution system, so that you also reduce the gas distribution system that people are sharing statewide, kind of from a cost perspective. So predicting the fuel source and system type is not the most easy thing in the world. So I had to collect data. So we don't really have a good sense of which buildings are gas and which buildings are electric. I had to collect data from Sacramento County building permit data, which goes back to around 2007, and kind of classify what permits were being installed as gas or electric water heating, et cetera. The Affordable Housing Committee, the Tax Credit Allocation Committee in California, provides capital needs assessments every time a low-income housing building goes through an upgrade. So they have pretty good data for kind of what are in these buildings, but there's not that many of them. And then we also were able to get some anonymized data from a previous SMUD multifamily program contractor, which left us with about 20% of meters of data. So we knew the HVAC and water heating fuel and system type for around 20% of those meters, and not many of the stove meters, which is fine because it's not a huge impact on the electric side of things. And so, interesting to note that most water heaters are gas. Most HVAC systems are gas as well. And because I think a lot of this data came from like more high-rise, like the low-income buildings tend to be more dense, mid-rise, high-rise buildings. There are a lot of central systems, and I think they're probably overrepresented in this data. So I used two methods to predict the fuel and system type of each building. So the first one, kind of the ideal solution, is to match like the total building load shapes for buildings that we don't know the fuel or system types to buildings that we do know. So at the bottom, you'll see different examples of average load shapes for buildings that say have electric space heating and individual electric water heating. So that because there's electric water heating, you have a higher base load because water heating is kind of running more consistently than space heating. Whereas on the right, you've just got an all gas building where your main variable load is your air conditioning. So trying to match those up is the ideal way to kind of identify what fuel types are in different buildings. But I also had to rely on multivariate imputation by chained equations, which is basically a machine learning method to predict the building attributes that I couldn't determine in the first method. So just using like area of building, number of units, et cetera, to kind of predict the unknown fuel and system types. So the outputs of that are in the second table below the post-imputed data. So as you can see, we have fewer central systems than in just like the known sample of data, just based on building, just a different stock of buildings, but still pretty similar numbers on the gas to electric ratio. And you'll just note that there's a higher percentage of gas buildings, kind of like, or more of the multifamily buildings are gas in downtown and south of downtown. And these also happen to be where the disadvantaged communities are located more so. So I don't have it explicitly stated here, but disadvantaged communities or multifamily buildings in disadvantaged communities tend to be have higher rates of gas end uses. So adding electrification measures, I basically used some load shapes that we developed internally at SMUD for electrification. So you'll see on the right there for heat pump water heaters, just individual heat pump water heaters. That's what the load shape looks like. I think you might find the central heat pump water heating shape a little surprising, but we found that it's pretty accurate. Just that central heat pump water heaters tend to run for around 16 to 20 hours a day. And then kind of, if it's uncontrolled, shut off at some point. So that tends to be in the morning when nobody's been using hot water. But then as people get up again around 7, 8, start taking showers, the central heat pump water heater turns back on to recharge. And there's also for heat pump HVAC systems, they provide an efficiency benefit over the previous air conditioning system because we're installing pretty efficient heat pumps and replacing not so efficient air conditioning systems that existed previously. So you'll see some negative kilowatt hour impacts in the summer months. And then just to see if there were any electrical infrastructure upgrades that could be avoided through passive efficiency measures like windows, roof and wall insulation, duct sealing. We applied an efficiency savings shape as well. So you can see that on the bottom right. So here is kind of what the transformer overloading and cost situation is. So based on information that we have at SMUD, the transmission and distribution planning team, we could use these pretty rough regressions on the right to estimate the cost of increasing transformer size to the next step. So basically just using that equation times the transformer size for pad mount. Pad mounts tend to be larger, and pole vaults are just the transformers you see up on poles, tend to be a little smaller. There are additional considerations. Some buildings have what we call direct bury, or distribution lines that have been buried underground, and these require trenching to replace if you got to replace the transformer. And so I added an extra cost in there, pretty consistent with what we see at SMUD. So around 20% of meters are on buildings that have direct bury, which is not a negligible amount. For panel overloading, I used the chart on the right, which we have at SMUD, to predict kind of the main service panel size in a building based on the transformer size in that building, and just use a cost estimate of size based on previous similar utility reporting, but there's definitely some uncertainty in these numbers. And a similar deal for the panel or the unit level panels, so like the panels in the units. I used the bottom right table to kind of predict unit panel size there based on the main service size per unit. So again, that's kind of an estimate based on an estimate. So there's a lot more uncertainty on the unit level panel size. And so we should take those numbers with a grain of salt. And so I assumed overloading was meant to be 1 hour above the rated size of the transformer or the panel, based on the load profile that we have. And so I also assumed that kVA was equivalent to kW for transformers, just to make it simple, and that amps times service voltage was equal to kW for the panels. So here are the results of the transformer loading cases. So I think I'll first point, there's a lot going on here, but I'll point you to the histogram on the right. You'll see that most transformers, that the peak load on most transformers is not above 70–75% of the rated size. That's good. Those transformers are in good shape. They're not overloaded. But there are about 10% that are in this 90% plus loading situation, which is not where you want to be. And so it's a non-negligible amount that are already overloaded. When we add electrification, you'll see that there's a little bit of an impact, but only ultimately 20 or less transformers out of around 5,000 that are connected to multifamily buildings are overloaded due specifically to electrification. Nonetheless, these are all transformers that we have to replace if we want to do electrification, so they're all worth considering. Something interesting is the efficiency measures that we added, the passive efficiency measures, do not help avoid any transformer upgrades. And this is partially because of the load shape. The load shape is not necessarily helping out at the peak hours in the peak months. So that's maybe one concern. If you used a different load shape, it might change a little bit, but for the most part, the transformers that are overloaded are way overloaded already. So just interesting that you're not going to be able to avoid them just with some energy efficiency. And just looking at the bottom bar chart, you'll just notice that, or box plot, sorry, that the overloading tends to happen in the summer months, like June, July, August. So that's where the brunt of we're not going to see a winter peak in Sacramento in multifamily buildings, at least. And so the main service panels are looking a little bit better. Even even fewer are overloaded, but or I should say a similar amount are overloaded, but many more have a lot more space on them, which is good to know. So about 10% are overloaded, and a few more of these are caused by electrification, interestingly, but still a lot of these are, they're overloaded from the start, as you can see there. And again, still really not any help from passive efficiency measures. And then the unit level, which again, take with a grain of salt, because I think these panel sizes are really, there's a lot of uncertainty in them. But we are seeing that like around 50% could be overloaded. And that's really where the biggest cost concern is, because if you have to, replace the panel in every single unit when you do an upgrade, that's really gonna jack up the costs of these projects. And so yeah, this could be the biggest kind of infrastructure cost. But again, a lot of uncertainty, and it's really hard to say before you go into a building whether or not you're going to need to do it. But I've tried to predict that here, and yeah, a lot of these buildings. But again, not many are caused by electrification. A lot of them were just already overloaded. So here's the total costs of these electrification projects. So per unit costs are what we have in this histogram on the top here. So the majority, around a third to 40% of unit project costs are going to be in the $12,000 to $14,000 range, and that's infrastructure, that's equipment, all inclusive, and that's about what you'd expect. That's I think about what you'd expect to pay on these projects. However, another 10% that are in this above $14,000 range, those can go as high as $20,000, $25,000 per unit, and that's when it starts becoming exorbitant. And those are the ones you really kind of want to avoid. You'll see in the table below, like the average costs per project again, are in the $10,000 range. And for low-income customers, both in low-income housing and on our low-income rate, the costs are even lower, which is good, both infrastructure and equipment costs. So that's just a good sign. Just it means we should look at targeting these, although consider the kind of additional impacts that might come along with this. Interestingly, in the disadvantaged communities, in the buildings in disadvantaged communities, the project costs are a little higher, but again, that's just because they are more likely to have more gas infrastructure that needs to be replaced, or gas equipment that needs to be replaced. And there are rebates available from SMUD that comprise about half of the project costs. So worth noting, I think that there are available rebates for these projects. So here are just where the project costs are the highest. So for infrastructure costs, I think interestingly, downtown is not seeing a lot of high per unit infrastructure costs. It's more in the outerlying areas, which is probably because these are less dense units or less dense complexes. So they're splitting, pretty big transformer costs across a smaller amount of units, whereas it's not as big of a deal downtown or an arcade area. But the equipment costs track pretty well, which is where the gas infrastructure is on the right there. You'll just see it's downtown. It's where the dense areas of Sacramento are for the most part. So the carbon savings, just a brief note. I didn't go too much into this, and this is maybe worth another study. But these are the carbon savings from these electrification upgrades. Most of the carbon comes from replacing gas systems with efficient electric systems on a pretty clean grid. So just removing those gas, the gas emissions. And I guess I should say these are tons of CO2 equivalent, because you're avoiding methane. I've got it wrong. It is tons of CO2. I'm not including methane leakage in this. So anyways, the total cost of all of these projects is around the $1 billion mark in Sacramento, which might sound like a lot, but if you spread that over 110,000 units over 25 years, it's really not a huge lift for something like this. because I think the electric infrastructure costs are not as bad as they could be, or as some people I think feared. And we end up, per carbon saving, so we're probably paying around total $470 per ton of carbon saving, which is a lot, but this is not including like the fact that you'd be paying to replace these systems at some point with like a gas boiler or a gas furnace, and these costs are not included here. So it's worth just keeping that in mind. And I'll wrap this up pretty shortly, but just wanted to check in on EVs because I know that's something we're also rolling out at SMUD. So it would be great to target buildings that have space on the transformer for EV chargers as well. And so just from looking at like, how many EVs per multifamily unit can a transformer handle? Almost half have space for, one charger per 2 multifamily units, which is, I think, really the goal. So you can certainly target a lot of these buildings with the transformers that are already in place and have to not really do any electrical upgrades to install chargers. But this is not my area of expertise, so this is just a little additional look. So conclusions from the study, about 55% of multifamily units in SMUD territory are all gas. This number is higher in disadvantaged communities. And so there's some air quality impact considerations there. About 10% of multifamily electrification projects are going to have, really just exorbitant electrical infrastructure costs. And it's going to be worth probably waiting to electrify these to just see if we get better at installing these, if panel prices drop as we begin needing to do this more, or if we find better solutions to this sort of thing. And passive efficiency is not enough to avoid these costs because most of these systems are already overloaded, not due to electrification. It's very possible to target neighborhoods, that have a combo of high density of gas appliances, low electrical constraints, maybe even enough room for EVs, and lower than average income or higher than average CalEnviro screen scores. And so I think there's ways to target that. I'll talk about some considerations that may make you not want to target that next, but and then just SMUD rebates are enough for many of these projects to make them competitive with like gas replacements. But there's additional opportunities for targeted rebates using state funding from the tech program and SB 350 in disadvantaged communities. Increased equipment availability, especially for central heat pump water heaters, as those prices drop, that'll be really helpful. And then just educating contractors and building owners. This will all increase the likelihood of electrification success. So next steps, I also want to look at the kind of statewide multifamily outlook. Are there similar rates of gas use statewide? Is it possible to use this study to model electrical constraints statewide? Not quite sure yet. But this is the more important one, I think. How is this going to impact the actual renters? Because I've really focused on the building owners who make the decision to electrify, but we don't want to electrify a building for a lot of money and then have that all get passed on to the renter in the building or the building occupant, especially if the bills increase. But it's worth noting that initial studies from E3 and SMUD have found that at least in SMUD territory, we're not going to see bill increases from electrification. More likely than not, we'll see bill decreases just because of SMUD's lower than average electric rates, but this won't be true statewide necessarily. And also just, I want to figure out how these costs get, how we don't want to price people out of houses, out of housing because they've gone electric, because that really exacerbates the equity issues. Like if you have to keep moving people, or if people have to keep moving into houses with gas infrastructure because it's cheaper, which have air quality impacts, it's something I really want to look at. And so that's a next step here. But yeah, that's it for me. Any questions?
All right, thank you, Rhys. Any questions for Rhys? Feel free to chat them or raise your hand, and you can unmute and talk with Rhys.
Yeah, Rhys, great presentation. I was curious whether your measurements on the panels and the transformers, you showed a lot of existing, like under the current regime, overload rates, pretty high overload rates, especially for the individual panels. But you had reason to be skeptical of that. But even the other panels, you showed a lot of overload. So do those numbers fit with kind of what you understand about like how likely it is for these panels and transformers to overload, and how does that impact your confidence in sort of the impact of electrification?
Yeah, I think it makes sense to me that just through, I think the way that buildings get like built and then added onto down the line, like either through poor or no calculations on like on installer parts, on the part of installers, I think it makes sense that about 10% of buildings have overloaded their electrical infrastructure just through increased occupancy, just added load as people add more appliances to their house or something. So I think it's not super surprising to me that around 10% were already overloaded. I was actually surprised that it was as low as that. I guess I was, based on other studies I had seen, it seemed possible to me that there would have been more transformers at the brink of overloading, but it was more so some were already way overloaded and most were not close to being overloaded.
Is there any like external validation you could do with those?
Yeah, I mean, they're like, the problem is, at least in SMUD territory, we haven't done a ton of electrification retrofits for multifamily buildings. So as we start doing that, and we are doing, more and more each year, it'd be interesting to validate like on a per building level, just like as we electrify a building, was I close on whether or not, because we do require, or SMUD does require people to do electrification loading study or like infrastructure loading studies before they add like a heat pump water heater. So, are their findings similar with mine, and does that give me confidence about whether my results are right for the rest of the building population? But right now, I'm looking for ways to validate it, but not quite sure how yet.
I guess I meant just validating the current overload estimate. Is that something you can validate?
It's not something that it's something that I haven't seen a lot of studies on. A few, like I know City of Palo Alto did a study on their transformers, but it's hard because it really changes depending on the age of infrastructure and the density of infrastructure. So it is, it's not something that I've found a way to verify or to validate yet, but it is important for me to be able to do that. So I'm still looking.
Yeah, unmuted. I think Sarah, I don't know if you're watching the chat there, Rhys, but Sarah had a couple of related questions about, what types of problems the overloading might be causing now pre-electrification, if that's anything that you've looked into or know about.
Yeah, in my discussions with like transmission and distribution planning folks, they're always been, I haven't heard of electrical fires or anything starting because of these overloading, but it is something that like SMUD at least is aware of, that a lot of their infrastructure is overloaded, and they're kind of working as quickly as they can to replace some of these transformers, because like SMUD, there's a balance of who will pay for the transformers. Like if a customer adds like a load that causes a transformer to overload, then the customer has to pay for it. But there are also situations in which SMUD has to pay for it. So SMUD is doing the transformers that are overloaded because of, I don't know, because of just general city growth. And so I guess all of this is to say, it sounds like there aren't like a lot of problems. Like I haven't heard of any huge problems caused by this, but it's something that SMUD is aware of. And you will see transformers fail as they are more and more overloaded. So it's something that SMUD is interested in replacing all of the transformers that are overloaded, I guess.
Excellent. I have one quick question, then we'll move on to Curtis. I guess I was wondering, you mentioned they haven't done a lot of electrification retrofits yet. I mean, I imagine logistically, it's somewhat challenging just because you're dealing with an owner and then all the renters, you have equipment and you have the infrastructure. So how are there plans for like how to make that? Do you have to, people can't cook for 2 weeks? How does that logistically like work?
Yeah, that's a great question. I didn't really touch on it here, but that's maybe one of the biggest barriers. Like if you have to replace a transformer, you're gonna have to cut power for at least like a day or something, and that nobody wants to do that. So that may be one of the bigger, like 2 days without electricity is as big of a deal as like the project costs, if not bigger. So really finding a way to kind of do just plug in these electrification retrofits is going to be key to this transition, because right now, yeah, it requires a whole lot of planning and kind of headaches. So I think that's it's hard to quantify those issues, but they are certainly important. So hopefully, as we get better at doing these electrification installs, it'll get easier.
Excellent. All right. Well, thanks, Rhys, so much for presenting. I'll put Rhys's email in the chat for anyone that wants to follow up. And then Curtis, if you're there, we will move on to you. All right.
Okay, how's it going?
There he is. All right.
Coming through okay?
Looks great.
All right, so thanks, Allie. Thanks everyone for coming today. My name is Curtis Harrington. I'm a senior engineer at the Western Cooling Efficiency Center, and I'm going to talk today about our project Aerosol envelope sealing of existing residences. So really quickly on the challenge that we're trying to address with this technology, the US residential building sector consumes 23% of all energy in the country. Space conditioning accounts for 43% of all that energy use, and air infiltration is responsible for about 30% of that space conditioning load. In addition, standard construction, our existing housing stock is quite leaky. If you look at the Lawrence Berkeley National Labs database on air leakage in buildings, you can see that the geometric mean result shows that the average is around 11 air changes per hour at 50 pascals. Putting that into perspective, there have been some recent standards that have come out to try to address envelope leakage by setting minimum standards. The International Energy Conservation Code started in 2012 with an envelope leakage requirement, and currently it's anywhere from 3 to 5 ACH 50, depending on your climate zone. The 5 ACH 50 is generally like Florida or very humid climate, so the 3 applies to much of the country. The DOE Zero Energy Ready program is another benchmark. They require 2 to 3 ACH 50, so even more stringent. And then there's even the passive house standard, which is not shown here, but it's 0.6 ACH 50. So clearly, in order to get our existing housing stock to close to these standards, we need to figure out a solution for sealing them. So there are current sealing methods that will get us to leakage levels that are shown there. However, there's issues with quality control. It adds cost and time, and there's training shortfalls in that area. Generally, the way it works is if you make the hole, you seal the hole in new construction. And so different trades are responsible for the overall air tightness of the building. There's not one vendor that's kind of responsible for that. So finding a reliable method for getting tighter envelopes is very much needed. So beyond the energy impacts, there's also health benefits for air sealing, and this applies especially in California, where the energy implications aren't quite as high as in the colder climates. But reducing transfer of contaminants and odors between multifamily units. When we compartmentalize apartments, you can improve comfort and air quality by reducing that air transfer. We've also measured sound transmission reduction when you seal the building, so there can be another comfort implication there. There's also the ability to better control outdoor air for ventilation purposes. So, you know, controlling PM 2.5 or ozone levels from outside and preventing those from getting in to the building. If you have a tight envelope, you can introduce ventilation air and treat it properly for health concerns. Obviously, you know, when all the wildfires were going off, everyone was trying to stay indoors. If the tighter the envelope, the better you can control those particulates from entering the space. And then lastly here, it facilitates the use of mechanical ventilation. So heat recovery ventilators and energy recovery ventilators are kind of the gold standard currently for ventilation systems. They have a supply and a return fan. They exchange heat with one another, so you're reducing the ventilation related load with those systems, but they're balanced. So putting an ERV and an HRV on a building doesn't reduce uncontrolled infiltration, and it might even make it worse relative to a building that's using exhaust only ventilation. Because once you balance that pressure with outside, then you're at the whim of the natural wind and stack effect causing infiltration. So if you're going to install those devices, you really need to have a tight envelope for them to work properly. So now I'm going to talk about the aerosol envelope sealing process, which I'm sure many of you are familiar with, but some may not. So first you start by you pressurize the building with a standard blower door technology, which is also used to measure air leakage in the building. So it measures the airflow being introduced to the building, the pressure across the envelope, and you can calculate how much leakage there is. While you're pressurizing the building, you inject an aerosol fog of sealant material. As air escapes through the various leaks in the building envelope, the sealant material particles are transported by the air to the leak where they impact and stick, ultimately forming a full seal. Because you're using a blower door to facilitate this entire process, you can also track the leakage in real time. So the contractor from outside the building can see the building ceiling. You can turn the machine off when you've reached a certain threshold that you're trying to reach, or when the process is no longer doing any sealing. There's a few photos on the bottom. The one in the middle here is from the Honda Smart Home. It shows, you know, someone came around with a bunch of foam and caulking to try to seal this building up. The aerosol found the little spot that they missed and sealed it up. And you'll also notice that there's not a bunch of gray sealant all over the building materials. It really just targeted that one location. So a little background on the sealant development history. We've been working on this technology for nearly 10 years now. In 2012, we did a small scale test for the Department of Energy Building America program. I show a little picture here of us in our office with a 4 by 8 foot box by 8 feet tall, and we put leaks distributed around that box. And we played with things like envelope pressure, application pressure, and particle size distribution to figure out the impacts of those variables. In 2013, we went to our first real home, a full-scale test. We worked with Habitat for Humanity in Stockton and sealed our first houses. We found from that work that we needed more than one injection point for the fog, for the aerosol fog. It wouldn't distribute properly without moving that thing around. So in order to not have it to go in the building during this process, we realized that we needed a multi-point injection system. So in 2014, we developed a multi-point injection system. It's shown here. You know, you have multiple nozzles spraying, distributing that aerosol. In 2016, we licensed the patent to Aerosol that sells it now under the trade name Aero Barrier. There are Aero Barrier dealers around the country now. You can pretty much get it anywhere in the country at this point. So yeah, so then in 2017, we sealed our first non-residential buildings. This is a project for the Department of Defense where we were at the Marine Corps base in Quantico, Virginia, and we sealed a small elementary school that was unoccupied at the time. 2018, Aero Barrier, Aeroseal developed the first commercial equipment. So instead of using our kind of machine that we built in the laboratory, there's this nice control box that controls the sealant injection flows, the computer controls, the fan controls, everything's housed in this box. And then in 2019, we just wrapped up a project for another Building America project where we evaluated the process on a production scale. This was in collaboration with the Center for Energy and Environment in Minneapolis. So we did this in both California and the Midwest, and we worked with builders to find the most appropriate time to apply this technology in their construction process. So we wanted to understand what's the least disruptive to the standard construction process, as well as what's the most effective in terms of air sealing. And then currently we're evaluating the process in existing homes. So that's the current project we have with Building America. Again, it's collaborating with the CEE in Minnesota, and that's what I'm going to talk about today. So the Building America project for existing homes, I talked about the process a little bit. It can seal gaps up to 5/8 of an inch or more perhaps, but really it works much more effectively and efficiently at smaller leak sizes and distributed leaks. So we're trying to target anything below 3/8 of an inch. If it's larger than that, then try to address that manually. As the leak gets bigger, it takes exponentially more time to seal. You don't want to be, because we're in existing buildings, we want to try to minimize the amount of time we're injecting the fog in the building. It takes about 1 to 2 hours of injection time. The new home project showed we were able to seal about 75% of the leakage on average. So that was a really good result. We've done some limited testing in existing buildings. Actually, one of the first houses we ever did was an existing building. However, this project's really going to address these key challenges that are posed by existing homes. Particularly, you need to protect all finished horizontal surfaces from sealant deposition. I mentioned, it only targets those leak sites, but it will fall onto the floor. So it doesn't stick to vertical surfaces or the ceiling, but it will fall out due to gravity. So you need to protect those surfaces. A process for identifying and manually sealing these larger leaks. We're also looking at some alternative sealants that dry clear, and then demonstrate how much leakage we're able to reduce in these buildings. A little bit more on the work scope. We're going to seal 35 homes between California and the Midwest. It applies to renovations, remodels, additions, and occupancy change. Basically, anytime the contents from the building are removed, we think that this process will work. We've been focusing on occupancy change for this project. It seems like the most, the most readily available kind of situation that we would find empty houses in. We could work with these groups. We haven't needed to, but essentially we work with housing authorities and affordable housing providers to identify, they own lots of properties, so they would know when buildings would become unoccupied. Remodelers would know, when a particular renovation might allow for this type of process to work. And then utility efficiency programs and time of sale programs. The utility is notified if someone's going to move out of a house because they turn their electricity off, and then someone else is coming in and they want to turn it on. So that would be an opportunity to approach the owner about doing this in that house while it's unoccupied. We want to develop these protocols for the pre-sealing and the surface protection in this project, any changes to the aerosol process. We're doing some work on sealants, as I mentioned, and then demonstrate the leakage reduction. And then see how far we can go towards an occupied house. Do we ever think it'll be possible to just pile up, couches and beds in the middle of the room and cover them with plastic? It's possible. I don't know if we'll get there in this project, but it's conceivable. All right, so now to some of the preliminary results for the California homes. We've sealed 11 homes so far, 5 single family and 6 apartments. The single family homes were all at time of tenant change. There's a couple shown here. They were all on raised foundations. A lot of houses out in the Sacramento Valley area are on slab built construction, but these all had crawl spaces underneath. And this implicates the surface preparation. Because if the floor itself leaks, you have to be really careful when you tape down the plastic covering the floor, that you don't allow any aerosol to get under that plastic and try to seal those leaks, because the whole point of putting that down is to prevent the floor from getting any sealant on it. If it's on a slab, you could put some plastic down and just kind of tack it down at various locations to make sure it's set. You need to be aware of combustion appliances that are in the house, not stoves so much, but water heaters or furnaces that are in the conditioned space. When you seal buildings and you have, say, an exhaust ventilation for the kitchen or the bathroom, when those fans turn on, if you have any reasonable depressurization of that, well, not any reasonable, if you have decent depressurization of that home because you have a tight envelope, you can produce a combustion safety problem in the house if you don't have adequate makeup air. So we do have to pay attention to some of these things when we're going out into existing buildings, beyond the fact that we also need to consider ventilation in older homes that maybe don't have it when you're sealing it up. And then the multifamily building that we worked with, all 6 of these apartments were in the same kind of building. There were 2 buildings that mirror images of each other. They were undergoing major renovation, and we had to work around other trades. So they were replacing floors, replacing HVAC, and doing paint. They were doing a numerous number of retrofits in this particular situation. So that was a bit of a challenge, but it ended up working out well. So here's some of the ceiling prep needed. I talked about covering the floors. You need to remove switch plates because we like to seal the electrical box rather than the plate to the wall. So you remove those and then replace them at the end. You need to protect operable windows. This is the same as in new construction. Any operable window, you want to make sure that those moving parts are not being covered in sealant and affecting the operation of that window. You need to cover appliances. So while these buildings are empty, a lot of times there's still stoves and refrigerators, there's countertops, of course, and those things you have to protect. And then fill the P-traps is something I wanted to note, because there was one house that was empty for longer than we had thought, and the toilets were completely empty and dry. And we ended up trying to seal the toilet, and it got pretty messy. So definitely fill the P-traps before you start the process is something we should remind everyone. And then this table here shows the person hours for all of the work required, broken into various portions. So generally, this has taken a team of 3 contractors, 1 to 2 days to do any of one of these jobs. But you can see the surface preparation takes the majority of the work. It takes upwards of a day for a full team of 3 to get the house prepped. The apartments were a completely different story. They were in major renovation. You can go in, we didn't have to protect the floors. It was much more like new construction. So minimal prep, 2 hours, and they were ready to go. Equipment setup, roughly 2 hours to move the stuff and get it in place and set nozzles and get everything going. In the apartments, we were able to set it up in a central location and seal 3 apartments from that one location. So it reduced the time for setup. The sealing takes 1 to 2 hours or so. There were a couple that took longer. Truckee had a bunch of issues with, there was HVAC ducts that were severed, and we weren't aware of that. And so there was just a bunch of weird things going on in that building that I think caused it to take a lot longer. In Hanson, this was a coastal house in Mendocino, and it was just very cool and humid climate. And that affects how much sealant injection you can inject into the building. So that's why that took longer. And then the cleanup time is fairly minimal. If you do a good job prepping the building, the cleanup is not too bad. It takes a couple of hours to clean up. So here's some photos of the preparation. You see the kitchen is all covered. The plastic is covering the appliances. You don't need to tape it down at the bottom because the aerosol doesn't want to travel upward, and we confirmed there was no leak sites behind it. This is a stairway that's ready for sealing. It's a carpeted stairway, and we have plastic on it. There's a interstitial building space behind it, so we expect there to be leakage through the carpet, and so you need to tape down around the plastic to make sure that sealant doesn't try to get in and through the carpet. Here's a living room completely prepped and ready to go. So there's plastic on the floor, it's taped down, there's tape around the windows. These ceiling fans are bagged up, and then the blower door is in place. Here's a bank of windows that are prepped and a sealant injection nozzle that's set up. So here's some example data from the first house that we sealed, the Lincoln house. This was built in 1900s, and it started at 12.6 ACH50, so a quite leaky home. And we got it down to 4.9 ACH50, representing a 62% reduction in air leakage in this home. This is really significant. I mean, this is a very leaky home. 4.9 ACH50, the California Building Code, if you follow the prescriptive plan for how to seal a new construction home, they expect you'll get about 5 ACH50. So we're getting this building to about what we'd expect new construction that's not going through any kind of advanced sealing methods to reach just by following the standard approach for sealing a building. Also, there's been, about 15 years of experience in the weatherization programs that had started a while ago. And what we've found is those sealing efforts that is a big part of the weatherization has ended up, you're doing good if you can seal 20 to 25% of the leakage of an existing home. So sealing 62% is a way beyond what we're able to do manually from our experience. It only required 41 minutes of injection time, so it was a really efficient sealing job. And then the big thing to point out is that the temporary seals covered a lot of leakage. There was 866 CFM at 50 pascals that was covered by that plastic, representing 4.1 ACH50. So a lot of this leakage was through the floor to the crawl space, and we can't address that with the aerosol when we cover the floor up. So there's clearly a lot more opportunity if you do some other retrofits, say, you finish the floors or you replace windows, you might be able to get this building even tighter. The top right plot shows the sealing profile. So the dots represent the house leakage as we go through the sealing process. It starts at 1800 CFM50 and it drops down to about 100 CFM50. So we're sealing 90% of the leakage that's available. That's about as good as we can expect from this process. And this line shows the rate of sealing, and that's shown on the secondary y-axis here. So at the beginning of the process, we're sealing about 85 CFM 50 every minute, and it drops down as the process continues until the building is no longer sealing at about 5 CFM 50 per minute. And then here is a summary of the air leakage testing results. So when we got to the building, we did a blower door test. We measured 12.6 ACH50. The prep dropped out by 4.1 or so. And then the aero barrier process went from that 8.5 down to below 1 ACH50. So we're approaching that passive house level. And then when you pick up the plastic, it bounces back up to the 4.9 that we ended up with. And here is a summary of all of the tests, except for the last 3 apartments. I haven't had a chance to put into this yet, but you see the Lincoln house here at the beginning, the Truckee house where we just had major issues throughout. It only sealed 20%, but I included that in the average. If you include all of this data, we saw that the leakage of the homes was about, on average, 10.5 ACH50. This agrees with kind of what LBNL's database suggests of 11 ACH50 as being typical for existing buildings. And then we ended at 4.5 on average for these homes. So we're getting these buildings to in line with current construction of new construction. The average leakage reduction was 57%. Again, quite good relative to other methods. And we should point out that that's including all of the significant leakage that we're not able to address because we're covering it and blocking it from sealant deposition. So this process, along with other retrofit measures, could get buildings quite tight. Here's some photos of seals that were produced. So the top left and the bottom right are some outlets showing a bunch of sealant deposition in those boxes. The center photo on the top is a can light that had fire foam applied all around it. You can see the aerosol found the small little gaps in the foam and that were missed. This is a plumbing penetration that we shoved some foam in here to kind of close up the big gaps and then allowed the aerosol to seal around it. This was just a super weird situation where there was like siding, building siding was the interior finish in this home on parts of it, and that ended up getting sealed up. In that same home, there was, this picture is kind of interesting because this is inside a wall cavity. There was a decent sized gap entering that wall cavity, and we stuck our phone inside and took a picture and found that the sealant found its way into the cavity and sealed up the various leaks within that wall cavity. So this reinforces that the sealant will find the leaks for you, which is why you need to spend, careful time prepping. You don't want to seal things that you don't want sealant on, or you don't want sealed, such as exhaust fans and so forth. But it will otherwise seal everything else, even if you're aware of it or not. So just ending on some upcoming efforts related to aerosol sealing. There's other things outside of the building world. There's some work in pipelines, but as far as homes and buildings, we're looking at sealing from the attic. So say an occupied building with things inside, we're looking at whether you can just spray in the attic space and suck it through the ceiling to at least address the leakage between the attic and the ceiling. Some studies have shown that can contribute about 50% of the entire air leakage of the building. So if we can, drop that leakage to say 40, if we can drop that leakage by 80 or 90%, then we can have a significant impact on the air leakage of the home. And then, okay, I talked about depressurizing it. And then the wall retrofit project. This is another strategy where we're looking at, it's kind of a niche thing where older buildings, older than 1970s, before the building code, there may be no insulation in the walls at all. We're trying to address that by adding insulation as well as some PCM product to try to reduce heating energy use. But we're going to start by seeing if we can do some aerosol sealing in those wall cavities. It would be a very different application. So there needs to be some work on how to distribute and apply that aerosol sealing. But this would essentially be able to seal up that wall as well as insulate and improve the performance of that wall overall. So that's all I have. If anyone has any questions, I'd be happy to take those now.
Perfect. Thanks, Curtis. Really interesting.
Sure.
I want to get my house signed up as a potential study site.
All right.
When you get ready for the residential ones, I'll sign myself up.
Okay.
I think David Potterson had a quick, just clarifying question in the chat. He was wondering if you said that infiltration is 30% of all space conditioning. He wanted to see, that was maybe your first slide. He just wanted to see if you got that right.
Yes. So I should caveat this statement. This includes ventilation for the building, but yes, 30% of the load in the building is due to outdoor air coming in, and so sometimes it's brought in on purpose through ventilation systems, but otherwise it's through uncontrolled infiltration. So if you were to put an HRV or ERV, this number would go down significantly because you would be exchanging that heat when you're ventilating your building. But infiltration still, regardless, if you don't have a tight building, you're going to have uncontrolled infiltration. But this includes both that and ventilation related loads.
Great. Any questions? Feel free to raise your hand or put them in the chat. I know we're bumping up right against the 1 o'clock hour. So if you need to run, that's fine. But if you have a few minutes, feel free to stick around and ask a question. No questions. Is there any cost information, Curtis? Like if someone were to do this, say this gets more, commercialized in the residential sector for home, like, is there any cost? I think I've seen data before from you on cost.
No? There is cost. So for this existing building project, it's hard to get a good idea of the cost because it's taking longer for our contractor to learn how to do these things. They've never really done existing buildings. We're still developing these processes, so he's working along with us. So these, even the time estimates that I showed was for I would say a novice team trying to figure this out. If we got really good at this and figured out exactly, how to focus our efforts, then the cost I would expect to come down. But just roughly, and it depends on how many, like an apartment complex or an apartment building, if you can do 100, say, compartmentalization ceilings, you're going to get a huge discount just because there's not all this travel of the trailer and getting the aero barrier equipment out there. But roughly, say for a new construction single family home, you're looking at maybe $1 to $1.50 a square foot. I would say that this existing is going to end up in the $2 to $2.50 kind of square footish range. That would be my guess, but you should really talk to the local aero barrier contractor, although they're not really doing this yet. So they're mainly focused on new construction currently. And I expect that, this project will go towards hopefully pushing them towards doing more existing.
All right, and we have one question here from Claire. Was wondering if there's any concerns with aerosols in the environment with this. I guess being, released into the air from maybe a health perspective, I guess, as well as environmental.
Yeah, I mean, there's no aerosol can sprays. A lot of times those are like HFC, like really bad for the environment. We're just using compressed air and we're spraying a water-based acrylic polymer. So the aerosol doesn't, wander outside and float around. It generally is contained within the building, and when you're done, it falls out due to gravity and you clean it up. So there's really no environmental impact beyond, having polymers and stuff out there has its own environmental implications. But the great thing about this process is because it only seals where leaks are, you're not wasting a bunch of polymers and other materials sealing things that aren't even really a leak, which you notice from that picture I showed of all the foaming. They just foamed everything, and foam is quite bad for the environment, and we all are aware of that. So I think that this process will actually end up being better for the environment as a whole and use less material if done properly.